Hello everyone and welcome. My name is Kristen Russell and I'll be one of your teachers for today's session. We are super excited to have all of you with us today and I hope that you will interact and participate as much as possible. We have a chat, we have polls, so there's lots of ways for you guys to let us know what you're thinking. I hope you're having a great Sunday and I hope that you are excited to learn a little bit more about the MCAT and maybe how to study for the MCAT. So let's take a look at today's agenda. So we're going to spend a little bit of time, me and all of you guys, talking about kind of what the MCAT's all about. So we're going to do a welcome and intro and a nice overview. Then I'll be handing you off to one of my colleagues and he'll be presenting to you guys an awesome lesson that has some strategy and some content in it. So I think you guys are going to love it. Then you'll come back with me and we'll talk a little bit more about how you can really implement some of the things that Brian's going to talk to you about into your studies, how to come up with a study plan, how to make sure you stay on track for how many months you're going to be studying, maybe even how long you need to study. We'll also be talking about scoring and what it's like to go from a low score to what ultimately you want to get on test day. So let's talk a little bit about why it's important to actually take the MCAT. So, I mean, what do you guys think? Why do people care about this? Well, we know that admissions committees really do care substantially about the MCAT. Actually, when polled to determine what is a really important factor in an applicant's package, admissions committees, a lot of them, as you can see here, over 50%, are saying that MCAT score is one of the most important things. Of course, undergrad GPA is up there as well. Now, if we think about why MCAT score is important, it's probably because a lot of you guys have very different backgrounds. Some of you guys might be going to a top 20 university. Some of you guys might be an English major, while others might be a biology major. So there are things that certainly are different in your application that might be hard for schools to compare. So this is a chance for everyone to be measured on exactly the same scale. That can be a little scary, especially if you're someone who has test anxiety. So it's something you certainly need to practice for. Now, I'm guessing, I'm going to go ahead and ask you, how many of you here right now have a 4.0 GPA? 4.0 GPA. Now, I'm willing to bet that some of you guys do. There's probably some of you in here who do, but I'm willing to bet that a lot of you don't. And that can be frustrating because in a few months, it's very, very hard to have a significant impact on your GPA. And as you can see here, it is a big factor to admissions committees. So of course, I think we all want to improve it. Now, I think if you spend 3 months working on your improvement, and so I think that's something you certainly want to focus your time on. Now, a lot of people ask the question, well, how much time? How much time do I need to spend? So we're going to talk about that a little bit more, but I'll go ahead and throw a number at you. 350 hours. That's how long you should spend total study time before the MCAT. In 2.5 months, others might need to take 8 months to fully study for this test. But 350 hours should be your target in total study time. Now that is an average. If you are a non-traditional student, if you had a different kind of major and you didn't do prereqs and now you're going back and learning things and you feel a little behind, it might take you more than 350. If you recently had all of these classes and they're extremely fresh on your mind, maybe you can go a little under, but that is a good place to start. Okay, so let's talk a little more in detail about what's tested on the MCAT. So there are 4 sections. 3 of the sections are science sections. So we have chemical and physical foundations of biological systems, which we refer to as Chem Phys. We have biological and biochemical foundations of living systems, Biochem, and psychological, social, and biological foundations of behavior, Psych-Soc. Each of those sections is 95 minutes long and has 59 questions. Of the 59 questions, 15 of those questions will be discretes. They're the standalone questions, and then you also have 10 passages. Then we have critical analysis and reasoning skills, also known as CARS. You have 90 minutes to do that. There are 53 questions that are spread across 9 passages. So what's your favorite section? I think a lot of students maybe start off liking biochem and Psych-Soc. A lot of people tend to do well in those initially. CARS is a section that I feel like a lot of people either hate it or they love it. And generally across the board, I find that a lot of people don't like Chem Phys. Now, you're lucky because Brian and I absolutely love Chem Phys, especially physics. So I find that a lot of pre-meds don't share that love, but Brian and I are going to try and share some of our passion with Chem Phys to you guys. So let's go ahead and talk a little more about science content and how it's really broken down by specific subject. So if you look at this, you can see a lot of dark blue. Well, that's good news for you biology majors or biology fans. So the #1 most tested science is biology. The #2 most tested science might be a surprise to some of you. It's actually psychology, and that's because it's tested so heavily on the psych-soc section. The #3 most tested science is biochemistry. So if you have not had biochem yet and you still have an opportunity to take biochem before the official MCAT, I highly recommend that you do that. If you can't, we do have some options, and you can certainly ask us about those to prep you for biochem at the same level one of your undergrad classes would. Now, I think, again, good news for those people that don't like physics. That's one of the least tested, along with organic chemistry is one of the least tested as well. Now, the MCAT's going to test you on a certain number of skills, and I want to talk to you briefly about those skills for the science sections. Skill 1. This is science knowledge. This is really your ability to recall scientific information. Skill 2, a little bit harder. This is where you're doing reasoning and problem solving. This is where most of your math questions are going to fall into. This is also where you're going to see some of the basic science concept tested in a new way. So maybe you're applying to a new system, just not the way you typically have seen that probably in some of your classes. So Skill 2 questions are very, very heavily tested, and they're pretty fun once you get used to them. Skill 3, we're looking at experimental and research design. So this is where you're getting questions about how an experiment is set up. Independent variables, sample and population, maybe things even with problems in the study. You also are going to know about research ethics in Skill 3. And finally, Skill 4, this is where you're looking at figure interpretation, basic statistics, but don't worry, you don't have to have a stats class. There are things like mean, median, mode, that kind of stuff. Now, we have an extra one on here. This isn't something that the AAMC says is one of their skills, but it's something we know is incredibly important when it comes to studying for this test, and it's being an MCAT expert. Knowing how they're going to test you, knowing the types of traps they're going to leave for you, knowing how to best approach problems. These are all things that are going to be super important. Instead of just content, you should be thinking strategy and how can I be an expert in exactly what they're going to test me on. So we're going to go ahead and switch you on over now. I'm going to go ahead and invite Brian on camera. Your journey to a higher score is about to begin, and I'm pretty excited to share the screen with him. He's going to have an awesome lesson to show you guys. And there he is. So I'm going to hop off and let him take it away. Have fun.
All right. Thank you very much, Kristen. Kristen is an amazing teacher. I always enjoy working with her. So I always throw love at all of my Kaplan coworkers, the moderators you have in the chat there. Kristen, they're just wonderful people, and I enjoy getting to work with them. The only thing I might enjoy maybe a little more than working with them is physics and physical science in general, but definitely physics. And so I am super excited to be here with you today to do some Chem Phys, which, as I said, it's all just physics. Some of it's just more applied than in other places. So what you're going to be seeing now is a portion taken out of one of our classes. This is Chem Phys sample class. It is actually taken from our Chem Phys first level class that you get as part of our class, as part of our course. So these classes start, as you're going to see, with a bit of high yield science before we dive into some serious strategy and the introductions of test taking strategy. So I get to be here for that with you, and I'm just always thrilled here because unlike many other Kaplan teachers, not all, but many, we have a lot of future doctors who work with us. I am not a future doctor. I am a science teacher. It is what I do, and I just love working with students like this. And so I'm excited for you to be near the beginning of your journey, perhaps, especially with those of you who are very new to the test today. And I just want to begin growing that love of physical science in you, as I'm sure many of you already have a love of the biological sciences. So first thing we're going to do here is we're going to take a look at stereoisomers. So stereoisomerism. And as Kristen was mentioning, with the skills the AMC states, I think a really cool thing they've done since when they introduced this change to the MCAT back in 2015 was be really outright about these are the skills we're testing. And the skills, while skill 1 is content knowledge. Do you know this isomer? Do you know this isomer? Do you know that isomer? Yeah, that's in there, but most students aren't actually struggling at that level by test day. The skill 1 is usually the first thing that they're most accustomed to studying and will get right most quickly. It's the rest of the skills. So you're going to see now, especially I'm really excited for those of you that are brand new to the MCAT, to really see how they can take content and make you have to think really critically about it. So let me just get a roll on here. So in this lesson, we're going to look at the different types, constitutional, conformational, and configurational isomers. Then we're going to be looking specifically at, in the instance we'll be observing, double bonds and how they relate to isomerism. And we'll also be looking at the difference between diastereomers and enantiomers, so the optical isomers. Wait a second. There's a big block of text on screen right now with a bunch of information that we're just giving to you. And then at the end of it, I'm going to ask you a question. And I'm going to lead you through this text, and then we're going to talk about this question. That's the way that our course works, because it's very important to be able to incorporate the information they give you and work with it and apply your content knowledge to a situation. This is in fact not even quite a full MCAT passage as you would be seeing on test day. This is just one of our introductory high-yield science things, but it's still the same general skill and idea of we've got a context in which I'm going to ask you to apply your scientific knowledge. We're given the context here of ibuprofen, one of my favorite medications for a multitude of injurious reasons that I've gone through in my past. But this is Advil, an NSAID, a non-steroidal anti-inflammatory drug, and it's taken to alleviate pain. Here's the part where we start getting into information that's actually worth noticing. Only one of its 2 isomers is biologically active. As you read information like that, I hope there's little sparks flying, neurons in your brains lighting up as you recognize that that's important, and that tells you some important things about ibuprofen. The active isomer was once isolated and marketed, but was withdrawn to its adverse side effects. People weren't taking into account the fact that it was much more potent, so they were taking too much. So now instead, we sell it as a mixture of both isomers, which once again, I'm sure there are things that are occurring to you there. And then we're presented with the structure. When given structures on test day, you don't want to spend a lot of time worrying about doing a detailed analysis of that structure right up front. It's not worth it. You analyze it when a question asks you. So I'm going to be asking you a question about it, and when we get there, then we will be answering questions about that structure. Interestingly, they said it's interesting. I should probably pay attention to it. In vivo testing reveals the existence of an isomerase, an enzyme, A's for enzyme, that is able to convert from one isomer to another. Converts 50 to 65% of the inactive isomer to the active isomer, but it requires bond breaking. Important clue there. So where does AMACR act on the ibuprofen molecule, and aside from their biological activity, how are these 2 isomers different from one another? So yes, I am absolutely certain that some of you are sitting there like hands on the keyboard about to type out a full explanation and answers. But I want to caution you about ways of studying for the MCAT. Being able to answer a question is not enough. You want to be able to answer lots of questions. You want to be able to take one thing you know and branch out from there and use it to hook on other information and put it as one group, one grouping of important content knowledge and interrelationships between that knowledge. So we're going to take more than just this question and answer it. We're going to branch out from there because that is one of the best ways to study. We're going to look at how not only this individual question is answered, but how it relates to why wrong answers that they could present with you here, for instance, would be wrong. So let's start by looking at the three classes of isomer. And we start with the conformational isomer. Then I'm going to ask you about configurational, then constitutional. As we go from left to right here for each one, we're looking at whether or not bonds get broken. We're looking at connectivity. Is it the same or is it different? Those are the two things that we want to evaluate about each of these three types. Conformational isomers are the first type we're going to look at, and we're given a Newman projection. Let me do this. There we go. We're given a Newman projection here. So in this Newman projection, we're looking down a single bond between two carbon molecules. And you should be able to tell me to go from one Newman projection here to another Newman projection, as we're looking at this, looks like a purple triol or something. As we look along this Newman projection, would we have to break a bond? Would we have to break bonds to go from one to another? So as you look at that, I hope you're thinking about, and as go ahead and answer me, I hope you're thinking about your ball and stick models that you were probably forced to buy in organic chemistry in college. And if you would build that molecule, you could have it one way, and then get to the other way. You would take one side, and you take the other side, and you would just twist around that bond. When you do that, no, you are not breaking bonds to go from one to the other. So all you're doing instead is rotating around that single bond. That rotation from one to the other, that's going from one conformational isomer to another. And this, in any given solution, in any given mixture that contains conformers, will be constantly happening. Because we know above absolute zero that all the atoms and molecules that make up any substance are in motion, and that's not just translocation. That's the atoms and molecules are wiggling, and if it's a molecule with bonds, it's shaking and vibrating a little bit. Excuse me. So that bond is going to twist. Now, there are some times where it's going to be more favorable than others. So in the one on the left here, that is absolutely the more favorable version than the one on the right, because there's less hindrance. You're going to be putting groups farther away from one another, but they will go back and forth. And otherwise, if you look atom to atom, every bond or every atom is bonded to the same other atoms between those two molecules. So their connectivities are exactly the same. They have exactly the same connectivity. So now let's go on to configurational isomers. And we're looking at these two, and I need to make sure you know about Fisher projections for this one. The one we're specifically looking for the Fisher projection on here is right here at that carbon, making a good little plus sign there. So with that plus sign there, that is where we're focusing for our Fisher projection, because that is a carbon bonded to a hydrogen, a methanol group, an alcohol group, and a methanol group, an aldehyde. So we have 4 different groups on that carbon. So 4 different groups on a carbon, we have a chiral carbon here. So with that chiral carbon, we could go through and do the designation. We're not going to bother right now because I hope you can see that these are mirror images of one another. That top aldehyde doesn't matter, the bottom methanol doesn't matter, but the positioning of the groups around that chiral carbon are mirrored from one another. And it's a non-superimposable mirror image. You couldn't just take that mirror and flip it over on the other one, because when a Fisher projection is drawn, it has to be giving you a grandmother hug. And I mean that referring to my own grandmother. Whenever my grandmother used to give us hugs, she would stab us with her glasses. It was just something my mom did. So she would hug you and she would like jab you with her glasses. So we all learned to hug mom like this. Arms as far forward as possible, head and body back so she could get a good hold of you and pull you in. So you'd give her a mum hug. So that's a Fisher projection. And if you flip over, like say you take this right molecule and you try and flip it over to put it on the left molecule, you could get the OH group on the right and the H group on the left and the aldehyde on the top and the methanol on the bottom. But the grandmother hug would be backwards. It would be going the wrong way. It would be like this instead of like this. And that's just not a hug. That's just not how the Fisher projection works. So you can't just put them in place of one another. You can't just spin around any bonds there. To go around from one to the other, you would have to break a bond. You would have to break a bond. You would have to take off the OH group or the H group and move it to the other side. So bond breaking is required. So they can't be conformational isomers. But other than that bond breaking, everything is to the same other thing. So we have the same, that chiral carbon has the same substituents. We have that same methanol at the top, methanol at the bottom, hydroxyl group and hydrogen attached to it. So it is a configurational isomer. So now on to the final one. The constitutional isomers. We have an aldehyde that has 2 alcohol groups on it, and we have a ketone with 2 alcohol groups on it, both with a 3-carbon chain. Those are going to have different properties. That an aldehyde and a ketone are going to behave differently. They're different things. So bond breaking is a definite here. To get that aldehyde or to get that carbonyl from a terminal to that middle carbon, that requires bond breaking. But that means also this is completely different connectivity. That central carbon has 2 bonds to oxygen in the right molecule, in the ketone, as a bond to oxygen and bond to hydrogen in the left molecule. So those are different connectivities. So that is a different molecule. So constitutional isomers, as we move to the right here and get to the constitutional isomers, you'll notice we have this arrow across the top. That arrow across the top with the down arrow thing. So we have decreasing what as we go from left to right there. Well, another way of saying constitutional isomers are the least what? Constitutional isomers are the least similar to one another. So there's decreasing similarity. Conformational isomers, then, they're basically the same thing. They are super similar. They're going to constantly go back and forth. Constitutional isomers, it's more of a coincidence that they have the same molecular formula. They don't necessarily have any functional groups in common just because they have the same atoms within them. So different connectivity, different bond breaking required. They're just completely different from one another. So constitutional isomers, there's not much to learn there besides they just have the same overall thing. And conformational isomer is going to be constantly going back and forth, and they're super similar to one another. But you do want to be familiar with how interchangeable they are and how there is a preference for less steric hindrance as they spin around. Configurational isomers are really the interesting, the super test-worthy ones. So let's talk about first why we know conformational and constitutional just aren't options here for the ibuprofen. So first and foremost, conformational isomers. Think about the things we were told. And which important piece of information that we picked up on while going through there means that the 2 different versions of ibuprofen could not be conformational isomers? Well, we had specifically two versions. We needed an isomer to go between them. Bond breaking was required. Those are specific things that mean that this could not be conformational isomers. It can't be conformational isomers if you have to break bonds to go between them. So with bond breaking, constitutional could still be an option though. So consider constitutional isomers. We were given a structure. We were given a name. We were told that they're ibuprofen. And we were told that both isomers are ibuprofen. If you think about the two examples of the constitutional isomers I put on there, they would have different names. One would be named as an aldehyde. The other would have been named as a ketone. Different name, different properties. They are just completely different molecules. These are both ibuprofen. So if they're both ibuprofen, they can't be the same, or they can't be constitutional isomers. They wouldn't have the same connectivity if they were different, constitutional isomers. So configurational isomers, they're basically where most test questions are going to lie anyway. We're going to want to really focus in on the configurational level. So now we're going to start narrowing it down within the constitutional isomers. First, the easiest thing to evaluate at this point is double bond isomerism. So isomerism that occurs across a double bond is cis-trans isomerism. So cis-trans, or archaically referred to as geometric, but we're going to refer to it as cis-trans. And easy isomerism, if that's what you're thinking as well, easy isomerism is a subtype of cis-trans isomerism. So we have to consider cis-trans isomerism. We have, well, there's cis-trans, and we've got the examples down here of trans-2-butene, where the thing that I remember messing me up when I first learned this was I would have thought, when I first learned this, I will admit this, I would have thought both of those were trans, because I thought it was, are they on the same side or on the opposite sides of the double bond based on the two lines I just drew there? And that's not how it works. Those aren't, if they were on opposite sides of that line, if it was different there, they would then be constitutional isomers. So that's not how it works. When we're talking about same side or opposite sides, we're talking about same sides or opposite sides of this line, of that line right there. So same side or opposite side of that line. Trans, the largest groups, so in this case a methyl and a methyl on the trans-2-butene and a methyl and the methyl on the cis-2-butene, are on opposite sides of that line that goes through the bond, or on the same side of the line that goes through the bond. So here's what we're given for ibuprofen. So I see double bonds. There are double bonds, so it's an option. So we have to look at these double bonds and consider, could those double bonds be a source of isomerism? Take a look at them. Could those be places where in one version of the ibuprofen molecule it is cis, and in another version of the ibuprofen molecule it is trans, or E and Z if they're more complex than a single non-hydrogen group on either side? If we look at that, we only have shown there, though I hope you recognize phenyl ring would mean resonance around that ring, we have shown 4 double bonds. So we consider those. Well, in the benzene ring in the center there, any ring structure, in order to make, think about NASCAR. NASCAR, I forget whether they're always turning left or always turning right. I'm pretty sure they're always turning left. In order to do a loop, you always have to turn in the same direction. So for an aromatic ring like that, all of those bonds have to keep turning the same direction. They have to be cis. They always have to be going that same way. So that means we can't have cis-trans isomerism happening at the benzene ring. Then, looking at the carboxylic acid carbonyl, well, in order to have cis-trans isomerism, we need it to have that double bond, have a group here, a group, maybe a hydrogen there, then have another group over here or on the other side and a hydrogen there. But with a carbonyl, we've got an oxygen on that side, and then it's just, these are lone pairs. Those lone pairs on the oxygen, they're, for one thing, they're the same thing, and for another, they don't really count as a bond. So you can't get isomerism based on the double bond of a carbonyl. There aren't substituents there in order to have them in different places. So, right there, we've eliminated the possibility of cis-trans isomerism being the difference between the two types of ibuprofen. So now we are down to optical. We're looking at either enantiomers or diastereomers. So, these must be enantiomers. Diastereomers, so optical diastereomers, require a certain number of chiral centers. And I want you to try and identify the chiral centers on this molecule. Take a moment, look through. Where are the chiral centers here? So the chiral centers here, we're looking for a carbon with 4 different things attached to it. So you should only be evaluating carbons that have, since we don't share the hydrogens here, you need a carbon that looks like this, because the 4th bond to that carbon will be a hydrogen. Then you need the carbon to look like that and have something different in positions 1, 2, and 3. Now, and I'm not doing priority there, I'm just calling them 1, 2, and 3. So when you look, there are only 2 possibilities coming up. There are only 2 places where you see that in this molecule. So here's the first one, and it's got a methyl, it goes down to the benzene, and it's got carboxylic acid, and then it would also have a hidden hydrogen. That's a chiral center. We've got chiral center number 1. So we, at this point, having eliminated conformational, constitutional, and cis-trans, for there to be isomerism here, there had to be a chiral center. It was a must. But if you would look down at the other one, if you would look down here, yeah, it is an sp3 hybridized carbon. It has only 1 hydrogen, but it has 2 methyl groups on it. Because it has 2 methyl groups, it doesn't have 4 different substituents. So that can't be it. That cannot be a chiral center. With only 1 chiral center, you can only have enantiomers. Diastereomers require minimum 2 chiral centers. The reason for that is because enantiomers, there we go. Let me type this out here just because it's worth having. Enantiomers are different at every chiral center. Diastereomers are different at least 1, but not all chiral centers. So if you only have 1, you're either different there or you're not. It's a binary decision. If you're different there, you're different at all of them. If you're not different there, it's the same molecule. So diastereomers could be different at 1, but not the other if you have 2. It could be different at 2 or 1, and not the other 1 or 2 if you have 3, but are impossible when there's only 1 chiral center. So yay, as I'm sure many of you recognized at the very beginning, we had enantiomers. But think about what we did. We just went through and refreshed your memory on all of the different interrelationships and worked through how we could definitively rule out all of the other types of isomerism. That's important. That is very important to be able to do. So, we were told that one of the isomers is biologically active. Well, that means the other is not, and that is biological activity and differences in them. That is one common way that you see enantiomers behave differently from one another, but it's not the big one. There's one thing that I'm sure you all, and go ahead and tell me, I'm sure you all immediately think as soon as you hear that you've got enantiomers. There's something they very specifically do differently from one another. So they are going to very specifically rotate plane polarized light in opposite directions. So they rotate plane polarized light. One will go right, one will go clockwise, the other will go counterclockwise. And okay, so if we've got R, which direction would that rotate plane polarized light? So if we have the R enantiomer of ibuprofen as opposed to the S enantiomer of ibuprofen, it's going to rotate plane polarized light. So light that only oscillates in one direction. Light that passes through that solution of the R ibuprofen would rotate, and here's the thing, I don't know, and you don't know. The only thing we know is that it rotates oppositely the S. Dex versus Lev tells us counterclockwise or clockwise or counterclockwise. But R and S must be experimentally determined. I'll tell you what, as a test writer, right there is one of my favorite things to trick students on. Yeah, right there. And Astrid, that's okay to mix it up. That is one of the things that they will try and get you on. And I want you to get questions wrong now. I want to ask you tricky questions now, the same tricky questions they'll ask you, so that on test day you get them right. Dex and Lev, those are clockwise and counterclockwise. R and S, yes. And D and L, those different conventions are so annoying, but D and L are right there with plus and minus. That's Dex and Lev. They tell you the direction that plane polarized light is rotated, but not whether it's R or S. R and S tell you which direction that it looks like from looking at the structure, but doesn't tell you the direction of rotating plane polarized light. So, keeping those separated, one you can get from the structure, R versus S. The other you get from experimentally looking at which way the light rotated, DL, or plus minus. But you must have one and then experimentally determine it to determine how they go together. The other difference we already said, the biological activity, that's how it behaves in a chiral environment. Because a lot of times our receptors to such chemicals are also enantiomers, are chiral. So they'll only respond to one or the other. Like my right hand will only fit in a right-handed glove. So if the right-handed glove is the receptor, my right hand can go in and activate that receptor, but my left hand will go, that doesn't work. So behavioral chiral environments is the other way. Glad you got it now. It's so important, and you know they're going to try and trick you on those things. All right. That's how we warm up our lessons at Kaplan. We start with the high yield science, and I just have so much fun on those. There are a few that I know I go way off on some awesome tangents that are entirely test related, but they're just such a good jumping off board for making connections. Right there, we could have answered that at the beginning. Hey, it has one chiral center. It can only have an enantiomer. Done. But that's not the way you want to learn. You want to learn the way we went through and we connected with all of the different types of isomerism there. That's the way to actually build lasting knowledge. And that's much of the way that the MCAT will test you, is with passage, where you have to apply things and see the connections between them. But now, Kristen mentioned the skills. I mentioned the skills. Skill 1 is the one that you're probably going to want to attack first. Unless you are really fresh out of every class, you're going to want to build that knowledge that then the skill 2, 3, and 4 acts upon. And then skill 5 really synthesizes it all together. So I want you to know content, but I also want you to be able to get that content out when you know it. So this is why it's a skill and not just knowledge. Because there are going to be times when you have the knowledge, You're going to look at questions you got wrong afterwards and go, oh, I knew that. Why didn't I knew that content. Why didn't I bring that up when I needed it? So we're going to talk about that here. We're going to see that in action. We're going to look at how you use clues and the thought process you go through. So you want to be activating. You want to be thinking this through. So in this part of the lesson now, time to recognize and recall the scientific principles exactly when they mention them. Sometimes they'll just say a principle and you want to bring it up. Sometimes there's something you've learned about in a science class. And I know this as a science teacher, as that is my background. One of the main things that many science teachers consider their job is to make you familiar with scientific principles. And it is an important part of their job, but I think the skill too is the more important part of a science teacher's job, but whatever. And we're going to ask you to recognize that scientific principle, those things that scientists have learned throughout history, given an example that principle can be used to explain. So those are the two versions of this that we're going to look at today. The specific topics that we're going to be looking at here. Stoichiometry, good bit of fun, very fundamental, very important stuff to be able to do, but there's good ways around actually having to do the hard work of it. Orgonomenclature, which I'm going to introduce the term. I want you to be smart lazy about orgonomenclature. If there's an orgonomenclature question, I want you to be smart lazy about it. And I'm going to tell you what, do not overestimate the MCAT. Sometimes they do ask questions as straightforward as orgonomenclature. We tend to think of them as these super huge, over-the-top questions, but there are questions that are just like as straightforward as, what was the independent variable in that experiment? They will ask some nice and straightforward questions. What is the name of that biological molecule? Then, get into the fun stuff. Thermo. And really getting to the true great physics here, fluids. I'm always disappointed that we don't just start out with the foundation of it all, electrostatics, and build from there. But I didn't build the entire course myself, so unfortunately I didn't get to stop that. So, the strategy here. And this is the thing. Strategy is underrated by most students as they begin their study of the MCAT. They begin with an overemphasis on just the knowledge, on just, do I know it? But there's even strategy behind being able to recall that. And you want the strategy to be consistent across the questions you attack. You don't want to think of it as a handyman with a giant toolbox where you have to go digging through that toolbox and pull out, I use this tool for this tool for this tool for this. You want to hone your strategy so it's more like a Swiss Army knife. It's got all of your tools all in one place. A multi-tool, like a Garmin, whatever it's called. A multi-tool that just does everything. It is all there and it can be used for any question. So that means that no matter how hard the question is, you start with a glance at the question. And I'm going to be taking you through questions where the pattern is, I look at the question from the bottom of the question to the top of the question. I don't mean read all of the answer choices carefully when I say start at the bottom, but I mean get a feel for what those answer choices look like. Then for those really giant questions they give you, only the end of the question is the actual question. So read that part first and decide what you actually need from the rest of it. This gives you an idea of what the topic is, how hard the question is going to be, and it really orients you to the question well. And that's consistent no matter how hard the question is. I go bottom to top. Then decide how you're going to attack the question. If it's a question that's attached to a passage, do you need the passage? Because sometimes you do, sometimes you don't. Do you need specific content knowledge that you have? Well, sometimes. Sometimes it's all given there to you. One common mistake is to underestimate the amount that's given to you in a passage. If you were staring at a question going, oh, I feel like I should know this, but I don't. A lot of students have been testing for so long in college, in high school, in middle school, even back in elementary school, where you're used to always having to have the answer up here. So you're used to going there all the time. Don't underestimate. If you feel like you should know it, but you don't, consider for a moment. Did they actually give this to me in the passage and I should just go back and find it? And also, this is the point where you consider what you actually need from that big block of text at the top of the question. Then you execute your plan. You come up with an idea of what you're going to do. Now you go about doing it. In the end, you want to say what the answer should look like. Sometimes that will be really specific. Hydrogen bonding is what I'm looking for, and you're going to go ahead and choose hydrogen bonding. Other times, well, I know transcription is the process by which mRNA is produced from DNA. We go through the hnRNA. You're going to activate some knowledge, but you're not going to think through every single possible thing that could be there. You're going to say, okay, these are the things I know. I'm going to think of a few important things, and then I'm going to attack the answer with those already in mind. The important thing is that when you go to the answers, you have put thought into it already. You aren't doing that thing that you've been doing probably for more than a decade, maybe even a couple decades at this point. Read the question and then immediately start reading the answers. Because when you do that, you're not taking the time to think. You're weighing the answers as if they all had an equal chance of being correct. If you put thought in ahead of time, you are searching for the right answer instead of evaluating all the answers. So, and there's actually a huge mental difference between searching for a right answer when you already have an idea of what would be in the right answer and evaluating all of the answers. Because evaluating all the answers is how you wind up, oh, I clicked the right one, then I changed my mind and I went to another one, or, oh man, I'm getting lost on this question. There's so many possibilities. These all sound so good. All of those things happen if you're considering all of the answer choices as if they have equal chance of being correct from this time you start reading them. So let's look outright at mentioned principles. As we are here in Chem Phys, now I want to do a Venn diagram here of which part of this is really physics, just because I have to. I want to emphasize something very important here. That should actually be the physics circle. Just, I have to emphasize, that should be the physics circle. The only reason it doesn't completely encompass organic chemistry is because I have to leave nomenclature out. Because nomenclature has more in common with Spanish or Latin than it does with physics. It is learning a foreign language. Otherwise, it's all just physics. It is all just physics. And I do that to be half joking here, but really, the reason I like to emphasize that is because when you build knowledge, build on, well, I understand this in physics, and that makes this in chemistry make more sense, which makes this in organic chemistry make more sense, which makes this in biochemistry make more sense, which makes this in biology make more sense. So it can all build and have a snowball effect. And I'll tell you right now, for those of you who are not the fans of physics that Kristen and I are, my least favorite science in college was Phys sucks. And that's how I referred to it. Physics sucks. I hated physics. Hands down, hated it at least as much as any of you did, or as any of you do. I love it now. And that's because I got past that memorizing formulas, equation sheet sort of physics, and went into, I really want to understand this. Once you get to the simplified understandings, you learn to love it. You really do. Anyway, off that soapbox now. Let's go into some questions. I hate when we put the word heat and transfer next to one another. It just hurts my brain. Heat is by definition. Heat is by definition a transfer. But so what is transferred and how? There's 3 specific types of heat. There are 3 specific types of heat. So heat is the transfer of thermal energy, very specifically thermal energy. So heat is the transfer of thermal energy from high temperature, always from high temperature to low temperature. That is foundational to all of thermodynamics. That is heat through and through, high temperature to low temperature at all times, and we just can't stop it. Even the best thermos won't stop it. So always from high temperature to low temperature, and it happens through 3 methods. So 3 different ways that we go from high temperature to low temperature. So, yeah, Rachel, exactly. Convection. Convection is bulk movement. It is a fluid must be heated from the bottom, So that lowers the density of that heated fluid, makes it less dense than its surroundings, and rises. Awesome. So we have, put them up here. I'll go in order in the slide just because they're top to bottom there, even though Rachel will start with convection. So radiation. One thing I know they're going to try and trap you on is confusing radiation and other places where you see an idea of radiation. When we say radiation in the context of heat, we have a very specific meaning. We mean electromagnetic spectrum radiation. Radio up through gamma radiation. This is photons. This is electromagnetic waves. So radiation. And here's the really cool thing. You, me, everything. And I really mean that. Everything. Everything that's above absolute zero, which is everything, really. We are all constantly emitting electromagnetic radiation. We are emitting light. This is how heat vision cameras work. They capture that infrared radiation that everything gives off. So a block of dry ice giving off infrared radiation. Less than I am, but it's still giving off the infrared radiation. Everything is. So that's why no matter how well you insulate it, it's still going to be cooling down just because it's emitting light. Then conduction. We've all experienced this at some point or another when we burn ourselves. So direct contact, if it is because of atoms or molecules hitting into other atoms or molecules, transferring thermal energy to them. And really, this is kinetic energy at a molecular level. So cool thing is conduction is actually work at an atomic level. It is work at an atomic level. So really, the only way to transfer energy is work, but we'll just say heat because it is a simplified version of work. It is a very specific version of work. So conduction is direct contact, and there must be direct contact to allow it. And convection. Convection is that fluid rising when it's heated and the cooled fluid sinks, so you get convection currents. Now, we had that clue, and question stems will have clues as to the relevant science content. In this case, the clue is the word heat. That word heat means we activate that science knowledge. Heat, conduction, convection, radiation. First thing that should come to mind when you hear heat, that's where it's the skill. You've drilled yourself to those things come up, conduction, convection, radiation. Then the next part of the skill is, how do those relate to the context I'm given? Sun's transfer of thermal energy to Earth. How does the sun... Notice I'm rephrasing the question in a way that makes more sense in my mind. That's another thing you always want to be doing. How does the sun's thermal energy reach the Earth? Well, I think through conduction, convection, and radiation. So conduction requires direct contact. Direct contact with the sun would be awful. Everything would be gone. Earth hits the sun, we're gone. Everything's gone. We're gone long before then. So that's not happening. Convection. Well, if there was a fluid convecting material from the sun to the Earth, that would mean that and then you would have convection current would be sinking back down to the sun again. There would be actual matter going from the sun to Earth, bringing that energy. It goes between here and there through space. Space is a distinct absence of matter. There's not a fluid there to convect. But as I'm sure many of you, if not all of you, jumped to, well, how does the thermal energy go from the sun to the Earth? Light. We think of visible light, but there's infrared, there's ultraviolet. It's the full spectrum of light. And light is radiation. Light is radiation. So we should be thinking that right away. Next. IPAC name. So, there's something that you have probably learned, and I think the slide even does this. First thing we animate here is identifying number of carbons in the backbone, but I want to emphasize something about this. Number of carbons in the backbone. To identify the backbone, you actually first have to identify where is the highest priority. where is the highest priority and the most electron withdrawn group, really. So typically carboxylic acid or carboxylic acid derivative, that carbon of the carboxylic acid or carboxylic acid derivative, if it's there, it's going to be highest priority. So be careful with that. Don't just start looking for longest chain. It's longest chain that has the highest priority group. So then you name that chain and you identify all the groups along the chain. But, and I know some of you have already started, some significant portion of you, because you are bright young ladies and gentlemen who really want to be doctors, you've already started naming this. I'll tell you what, on the MCAT, there's no partial credit. There's no showing your work. There's only choosing the right answer, and I want you to be lazy as possible. I want you to be intelligently lazy. So we're not going to name this molecule. We're not going to name that molecule. We're going to come back, and don't worry, for all of them, we're going to see the answers. We're going to go back and see the answers, but we're not going to outright name that molecule. Next, we have an outright question asking us about liquids but not gases. When they say liquids and gases and leave out the third state of matter, solids, like the table, but we're asking about liquids like water or gases like air. So liquids and gases are both fluids. That means that they're able to flow. But there's an important distinction between those two. They have a lot of things in common as fluids, but there's a very important distinction that you want to keep in mind between liquids and gases. So, as fluids, they can flow. They have free movement of atoms past one another. They both will take the shape of the container they're in there for. But liquids, on the MCAT, you cannot compress a liquid. The particles are more dense. They're closer together. So you can't compress them anymore, and they will not spread out if you alleviate the pressure on them. You could lead to a phase change, but you will not cause the liquid itself to spread. They are not compressible. Gases will take up all the space they are given. So they are the least dense, they have the greatest particle speed, and they will take up all the space they are given. So they are compressible. You make the container this big, they will take up that space. You make the container that big, they will take up that space. And now, we're asked about hydrostatic pressure. Physics. Now the pure physics for us. Hydrostatic pressure is our content, is our topic clue right off the bat. So, we're asked about hydrostatic pressure, but we're asked about plots. And I'm just going to tell you right now, because this is something you would notice if you were actually attacking this question with the answer choices there. The answer choices are all graphs, are all line graphs, showing one labeled as Earth and one labeled as the Moon. And I know you all know something about line graphs. I know you all know how to graph a line. If I asked you to graph a line, you would either want to know a couple points on the line, or you would want to know a specific equation. Because we all had that drilled into us, I think in early middle school, then over and over again in high school, and you're still using it through so many science classes, even upper level math classes. You will still always be making use of slope-intercept. So that's something that should always occur to you anytime you're asked about any sort of line. But then hydrostatic pressure. Well, hydrostatic pressure is going to be plotted on a line graph. So I need to think about what I know about hydrostatic pressure. Well, first, yes, you will want to know the equation. But to help you learn equations, it's better to think through what factors, what variables should be in that equation. What things, if they changed, would lead to a different pressure, a different hydrostatic pressure. So, so the hydrostatic pressure, what I want you to think of it as is at any given location, it is the weight, the total weight of fluid above a certain area. So if you're looking at newtons per square meter like the Pascal, it would be the weight in newtons above a square meter of that fluid at that location at that depth. So That right there, I said the things that go into it, right? You need to know, well, the fluid above you, you need to know how much is there. You need to know how dense it is. So that's this equation right here. Trap number 1. Single most common mistake. Forgetting P naught. Not peanut, P naught. P naught, that at the surface of the fluid. If there's another fluid above it, it's okay, what's the weight from all the fluid above it? We commonly see this when you're in the ocean or a swimming pool or something. There's the atmosphere above the water you're in. So the atmosphere is causing 1 atmosphere of pressure, and you have to add that on. It's very common to forget that. Second most common mistake. This density right here is the density of the fluid. If you take density times gravity times height, what you're doing is finding the weight of the fluid above that square meter, because density times gravity times height, that's going to be mass times gravity. Just the way the units cancel. All right, so we'll come back to all of those questions now. Let's circle back around. So, I get to sit back for a moment. I want to put a poll down beneath now. And I want you to tell me, what is the primary way the sun's thermal energy is transferred to the Earth? So what is the way? I don't even want to say primary way. I want to say the way. What is the way the sun's thermal energy transfers to the Earth? And there's a great trap here, because consider there are only 300. There are only 3 types of heat. Only 3 types of heat. They have to have a trap answer in there, and I'm so thrilled that none of you fell for it. We said earlier, well, it has to be radiation. Has to be radiation. But nobody got mixed up going from one to the other and chose radioactivity. They needed that 4th answer there, so they're going to choose a tricky 4th answer. One that looks similar to the right answer, and there it is. Radioactivity does not necessarily mean heat, electromagnetic radiation. All right, so you nailed that one. In fact, 100% of you got that one right. And that means star time. Because honestly, no matter how old you get, you enjoy giving and receiving gold stars. Excellent work. Very good. All right, let's see if we can keep that trend up as we make things more difficult. So, for this one, though, I do not want you to dive into answering it. I want you to consider, do you really need to do the thing that you're all inclined to do and start building out this molecule? No, you do not. You do not. The answer choices give you a lot of information. The answer choices, look at the differences between them. It's what we refer to as a 2 by 2. 2 by 2. What that means is they are really different in 2 places with 2 options. We have chloro or dichloro, chloro or dichloro. And we have whether the butene is in front or the butene is at the back. All right. In this case, well, let me first make sure we get this. This is an ester. This is an ester. Aunt Esther is a kook. She always likes to drink Coors, and she spouts out crazy stuff. That is an ester. The way to properly write out an ester, and you can confirm this here by counting how many things are attached to the carbons, would be like this. So typically when it's written out, the one on the left is with the carbonyl. The one on the left has the carbonyl. I want to go in, I want to change this question, flip it the other way around, because The 4-carbon chain on the right here, therefore, I would move this up, has the carbonyl, which means it is the backbone. The backbone is 4-carbon. If it had been the other way around, and the double bond to oxygen, the carbonyl, had been on a methyl, and the other side had been a butyl, the methyl would get priority. Yeah, Francis, so many fun ways to remember things, and I will say some crazy things to get my students to remember stuff. You should hear me, because I'm completely tone deaf, sing Twinkle, Twinkle, Little Star, V is equal to IR to make sure they get Ohm's Law. So, and I lost my voice, so I really can't sing it right now. So here, it is the butyl that should get priority. So because the butte gets priority, and it is a beauty, go away that stuff, there we go, then yeah, we can eliminate that C and D. The next thing is we should have 2 chlorines. It should be a dichloro. Dichloro. Not chloro, dichloro. Dichloro means it's B. So wait a second. Of all the characteristics here, the fact that it was an ester, well, you did need to know that for the priority of giving the butyl priority, but you didn't have to remember how to name an ester as an O8 because that was already given to you. I would be willing to bet that a significant portion of you didn't even notice that the butyl chain is actually a butene O8, even though it's in every answer, because it's in every answer. It doesn't matter that there is a double bond in the middle of that 4-carbon chain. It simply doesn't matter to getting this question right. This was not an open-ended question. This was not a, I'm going to give you the structure and you write out the name and you better get it perfectly right. The MCAT is a multiple choice test. Use those choices to your advantage. Be lazy. Be super lazy. I'm sorry to say no gold star here, but still, take everything you can from that. All right, liquids but not true of gases. All right, in the poll, I'm going to give you a moment to do this one in the poll for me. Remembering that liquids and gases are both fluids. Liquids and gases both fluids. That means they flow. But we want something that is true of liquids, but not true of gases. All right, excellent, excellent. So, as a significant proportion of you, but not golden star levels, have gotten, liquids, we want to absolutely know, are not compressible. They are essentially incompressible. B is the right answer. When you chose that on test day, I would not want you looking through those wrong answers, because not everyone got this right. And I am sure that somebody got this wrong, because even though they saw B, they kept reading. They saw something that caught their attention. They chose it. And they forgot that we'd already predicted that the big difference is that liquids cannot be compressed. They do not take their entire container, but gases do. All right, now, hydrostatic pressure. I want to put this in as reminding you one more time. Hydrostatic pressure is about the weight of fluid above you. It is about the weight of fluid above you. So in the poll, which one would correctly show as you've got pressure versus as you go downward in a liquid, depth in a liquid, for Earth versus the moon? I will admit there's some hidden content knowledge here. Hidden content knowledge you do need to know. Earth has more gravity. Earth has more gravity than the moon. The moon has basically no atmosphere. The moon has no atmosphere. the MCAT's kind of assuming we know that. It's like hidden content knowledge. So if you think of it as weight of fluid above you, and you're picturing Neil Armstrong jumping around on the moon, if you're picturing dropping the rock and the feather on the moon, so especially the hammer and the feather, that's such a good example because it shows both the lack of atmosphere and the difference in gravity. They fall slowly on the moon, and you don't get resistance for you don't get resistance against that feather. Well, let's connect that P naught plus rho gh. And I told you line graphs mean slope intercept, y equals mx plus b. But b is our place where x, or in this case z, equals 0. So that would be the pressure at the surface of the fluid. That is atmospheric pressure. So b would be P naught, would be atmospheric pressure. So that means Earth with an atmosphere should have a higher y-intercept, b being the y-intercept. Go away C, go away B. And then the M. Well, H is equivalent to Z. H is equivalent to Z, is equivalent to X, is our x-axis. So H is our depth. And that means rho g. Well, if it's a liquid, we're assuming it's the same liquid, so we can kind of ignore the rho because that's a constant. So the difference is really g. So g, gravity, is our m in our slope-intercept equation. So Earth with more gravity should have a higher m, and m is slope. And now, as gold star worthy numbers of you have said, the correct answer therefore is A, because that's the one that says Earth has a steeper slope. You are perfectly fine if you work it out that way. I jump to this answer by saying, well, I know things are always heavier on Earth than they are on the moon. So I want the answer that always shows the Earth line above the moon line, because pressure is weight. It is weight of fluid above you. So things weigh more on Earth, so I always want to be higher on Earth. A is the only one that shows the Earth line always above the moon line. Choose A and keep going. So awesome work on that one. All right. Now, last set I get to do with you. Now, instead of outright stating scientific principles, so last time we said heat, we said hydrostatic pressure. Now I'm going to give you an example, and this is now really stepping up what impresses a lot of people when you talk to a scientist. A scientist is able to recognize the principles with which they're very familiar, and given a situation, just apply them to that situation, and it makes them able to make conclusions based on theoretical frameworks in their mind. The AMC expects you to be able to do that because that's what doctors do. You are given an example, aka a patient, and you apply your framework, your theoretical framework that you learned throughout med school to that person, to that patient. So here, let's start with this one. We're talking about monatomic ideal gas. So we're trying to figure out what is the topic, what is the umbrella under which we are hiding here. So we got monatomic ideal gas. We have isothermal compression and adiabatic expansion. So with all of that, those are our clues, because there are always going to be clues. Sometimes there are red herrings. There are clues that point to other things, but those clues all point in the same direction. Those clues point at thermo. Yes, thermo. So I love thermo, but I know a lot of students struggle with thermo. We have an awesome thing called the MCAT channel on which Kristen does teaching. Yeah, exactly, Astrid. So we have a bunch of awesome teachers who teach on the MCAT channel, and one of the best sessions on our MCAT channel, which is something our classroom students get access to, is the thermodynamics sessions. They are spectacular, and they really take students from going, I hate thermo, to, wait, that's all my professor was trying to say? Why do they have to make it sound so hard? So I want to take you a little bit down that path of, wait, that's what they were trying to say? But I don't have the time, because the thermodynamics channel session is a full hour dedicated to thermo. I think there are actually two of them. One is introduction, the other is application. But I want to give you a taste of it. So thermo, I love it. You do want to know some equations, but you want to know Pivnert. Absolutely know that for ideal gases. You want to know what U is. U is our generic letter that represents energy. The internal energy of a system is equal to 3/2 times pressure times volume, or is 3/2 times the number of moles times R, the gas constant, times T. Really, the big connection here, the way we measure the internal energy of a system is with temperature. Thermo measures, like a thermometer, right? Thermo measures the internal energy of a system with temperature. So if a system gains internal energy, its temperature goes up. If a system loses internal energy, its temperature goes down in thermodynamics. There's a lot more complexity to that in the world of thermo, but that's the simplification we can work with at this level. But this right here, this middle equation, is the one I love most. I always fix it and get rid of that stupid convention that some physicists a long time ago put on us, just like Ben Franklin mixed us up with the direction of charge movement, that work by the system. That's going back to steam engines, because we use the systems to do work. That's the reason we always do minus work by the system. But what I want you to know that really says, that equation is just a fancy way of saying the only to transfer energy are through work and heat. Heat is conduction, convection, and radiation, as we went through, and work is a force applied for a distance. Work is a force applied for a distance. So I want to put a little more on here. The way a system, because when we're talking about these, we're talking about gas systems. The way systems do work or have work done on them is by changing volume. That's the other important thing you have to understand for this all to make any sense whatsoever. Expansions always remove energy from the system through work. So in an expansion, the system does work. That's why it's minus work by. In a compression, work has to be done on the system. It transfers energy in. Compressions always transfer energy into the system through work. Always. Now, the system doesn't necessarily gain or lose energy because of the presence of heat. So you can have more heat or less heat. You can have the same heat. And that's where we get into the ideas of adiabatic, isothermal, and all that stuff. And I'll pop those definitions on screen when I ask you to answer this question. But you want to keep in mind, we have an expansion. That means work moved energy out. And we have a compression, which means work moved energy in. But you have to understand what heat did in those situations to be able to answer this question. So that I'll put up on screen after we go over a couple others. Here it is not outright said, but there's a great clue. So what is our topic to this question? What is the skill? What is the title of the chapter in our science textbook that would teach us about how to answer this question? So as you look through, we're given grams of iron sulfide and iron and sulfur, and we're told there's some unreacted chemicals left over. That leftover thing, leftover is our clue. This is a question about stoichiometry. This is a question about balancing the reaction, seeing how many moles we have, and then seeing which one is our limiting reagent. So, steps are, and I want to simplify this. 1, balance. 2, find moles of reactants. And 3, divide moles over coefficient, smallest value is limiting. Stiochem. That sounds like an awesome version of OChem. Stiochem. Stoichiometry. Excuse me, sorry. Stoichiometry. So, but this is right up there with orgonomenclature, where I don't want to do the work on this one. We're going to aim to we're going to aim to be lazy here. I aim to be intelligently lazy at every opportunity. Every opportunity. So we're going to aim to be lazy when we actually attack this question. Same thing on this one. Same thing on this one. We've got this giant setup. We have a child playing blah, blah. Don't read all that. We're trying to figure out what is the actual part of this thing that is the relevant, important content. And as we go into this, I start, as I said, at the bottom. Why does this happen is what we're being asked. Okay, that's not very useful, except for the pronoun this. Why does what happen? We are being asked to explain why a balloon sinks. And it's upon squeezing, but the actual event we're being asked to explain is sinking. Sinking, this means fluids, but this specifically means buoyancy. So there's lots of different stuff we could go into here, but this is the one that actually matters. There's Pascal hidden in within this, there's gas law within this, but the only one that outright matters, and then we can determine whether the rest of it matters, is buoyancy. If something was floating, less dense than, I spelled dense as dance at first. I can't believe I did that. Less dense than fluid it was in. If it was floating, it was less dense. If it then sank, became more dense than fluid it was in. Fluid dynamics. So, to become more dense, that is the only way we can possibly explain something that was floating becoming sinking. It's the only possible way. That is it. It must have been that it became more dense. That would be my first level of attacking the question. And first and foremost, I need the thing that sank, in this case the balloon. The balloon needed to become more dense. That's it. Then I can evaluate the rest of, okay, if they all say it became more dense, but they give different mechanisms, then I have to look at the rest of the information and evaluate it. But first and foremost, it became more dense. So I want to give you a moment here. I've put up the definitions, and you can tell me in the poll. I've put up the definitions of isothermal. No change in temperature. No change in temperature means no change in internal energy. Isobaric means no change in pressure. Isovolumetric or isochoric means no change in volume. That also therefore means work equals 0. There's no work. There's no change in volume means there's no work. And if it's adiabatic, there's no heat in or out of the system. That means Q equals 0. Q equals 0. Those are important definitions. And isothermal would mean that U equals 0. Or I should say delta U, not U. Not going to be U equals 0. Delta U equals 0. So, let's work this through. We have an adiabatic expansion. Adiabatic expansion first. Adiabatic means U equals 0. Expansion means energy removed by work. Q equals 0 because it's adiabatic. Energy lost to work because expansion. So I'm breaking down how my mind translates the term adiabatic expansion. It tells me that phrase. Which means if you have energy is lost through work and no change through heat, that means delta U is negative. Delta U must be negative. The system lost energy. Temp down. Then, that's step 1. Now step 2, we have step 2, we have an isothermal compression. Isothermal compression, I said there's no change in energy. Delta U equals 0, and that's because even though it's a compression, work in is canceled by heat out. That must be true for an isothermal compression. Any work that is done in one direction is canceled by heat in the other direction. So first we have energy go down. Then we have energy stay constant. First energy goes down, then energy stays constant. One of these says that. If energy first goes down, then stays constant, that means in the end, it has less energy than it originally did. That is C. That is C. So let's, because A, B, and C, you were torn between the three of them. A, heat input into the gas is 0. Well, we don't know that. First, there was no heat transfer, but then there was heat out. So in fact, it would definitely not be no net heat. Then net work done by the gas is not going to be 0 because while it's a compression, then an expansion, then a compression, they're not necessarily going to cancel each other because they're not the same magnitudes. Here's a good trick. C and D are actually perfectly opposite answer choices. Final state has a lower internal energy, or final state has a higher average temperature. Remember, temperature measures energy. Since C and D are perfect opposite answer choices, best odds are that one of them is the right answer. 50-50 between the two of them. C is the right answer. It would be a colder gas afterwards. So C is the right answer. All right. We don't do the work on a question like this. We are lazy. Lazy, lazy, lazy. Look at these answer choices and you see some serious patterns. We're reacting iron with sulfur to produce iron hydroxide, or iron sulfide, iron sulfide, and we're asked how much is left over. The answer choices have either 8 grams of one, 8 grams of the other, 8 grams of the other, or 8 grams of each. Okay, one of these is completely unreasonable and we should eliminate. When you have a limiting reagent, you're going to leave over 1. If they're in stoichiometric ratios, so there is no limiting reagent, we wouldn't have left over. D is an unreasonable statement. That wouldn't happen. Those 8 grams of each, they would continue to react. Then, look between A, B, and C, the differences between them. Evaluate these differences. Fewer moles, more moles, and less mass. Wait a second. Which one are we supposed to look at? Mass or moles when we're doing stoichiometry? Should we evaluate the mass or should we evaluate the moles? Well, you can use mass to calculate moles. Yeah, exactly. Mass is not what we go by. So before we dive into any math, let's get rid of that other unreasonable answer. So we get rid of C. All right, now we're left with A and B. One says iron, one says sulfur. But they both say 8 grams left. But there's another difference here. Fewer moles or more moles? Does the thing that gets left over get left over because there are fewer, or does it get left over because there's more? Does the thing that gets left over get left over because there's fewer moles of it, or because there's more moles of it? Well, if I have a plate of crackers and cheese, and I put a cracker and a slice of cheese together, and I started out with more cheese than crackers, I'm going to have cheese left over on my plate at the end. Can you tell I'm really hungry right now? Cheese and crackers. Anyway, yeah, the thing that's left over is the thing that you have more of. You don't get left over because there are fewer moles. That doesn't work that way. Exactly, Ellie. Exactly, Moza. So, B must be the right answer. I want you to think about that for a moment. Look what they were trying to get you to do. They wanted you to calculate the moles of iron, the moles of sulfur, based on that. They wanted you to make sure you were conscious that, okay, iron sulfide would mean 1-to-1 stoichiometric ratios. They wanted you to actually bother to write out the equation. Fe plus S yields FeS. They wanted you to then take moles of each, divide it by 1, and see that, well, the one that I start with fewer moles. Oh, wait a second. So the fewer moles is the limiting reagent, so the one that I had more moles of is left over. Oh, B is the right answer. But think about all that time wasted. So much time wasted. Choose B. Celebrate. Celebrate your laziness. I celebrate my laziness all the time. It sounds awful, but I do. And let's move on to one more question. I gave you the way to answer this. Follow through on it. Stick to what we said. Tell me in the poll. For number 7. Why does the balloon sink? Why does the balloon sink? When you find that answer, do not keep reading the wrong answers because you will wind up getting trapped and change your answer to something else. There is one right answer. It is what we said it would be. Find it, go with it. All right. This can be a time-consuming question. This can be a difficult question. But you all, well, not all, but enough of you to get a gold star. Well, it dropped a little bit, but I'm still going to give you the gold star because it's a tough question. Got A. We said, when we went through this, we said, well, the only reason anything ever sinks is because it's more dense than the fluid it's in. So for something to be floating, it was less dense. Then sink had to become more dense. Well, we need it to sink. We need its density to go up. Hey, I see two answers that use the word density. And I see one saying that increase the density of the balloon. The other says increase the density of the water. No, that's not what we said. We said increase the density of the balloon. The correct answer must be A. No question, has to be A. So now there's all kinds of cool science behind this. And this, I have one of these in my classroom at my school where we do this. So what happens is you squeeze the bottle, the pressure gets transmitted undiminished through the water that's in the bottle, and it compresses the balloon. That pressure is applied to the balloon, but the balloon has air in it, and air is compressible. So that increases the density of the balloon because you increase the density of the air, and it also has the latex of the balloon around it, which now it has become more dense than the water, and it will sink. All we need to say is the balloon's density went up, and we get the right answer, A. B is such a great trap because you're compressing it. You're saying the water is compressed, so yeah, it sounds good. And the buoyant force is thus increased. No. Yeah, exactly as Astrid said, the buoyant force pushes up. The buoyant force actually doesn't, well, the buoyant force would actually go down because we decrease the density, or we decrease the volume. And buoyant force is equal to the weight of fluid displaced. So by shrinking that balloon, it's now displacing less water. And because it's displacing less water, there's less buoyant force on it pushing up. So now the weight of the balloon doesn't change. There's still as much matter there. But its weight still going down, the buoyant force up is less, so it sinks. Yeah. Liquids are not compressible. We can apply pressure to them, but their volume doesn't change. So by compressing it, we apply pressure to it, but we do not change its volume. It is the balloon that gets compressed that has its volume actually change as a result of the pressure being applied to it. So correct answer is A. Yeah, water in the bottle is compressed. Yeah, that doesn't happen. Liquids are not compressible. So that would be a reason to eliminate B right away. All right. So I'm at the end of what I have. That means time to Brady Bunch style return you back over to Kristen. So what we've gone over here, and I want to make sure you've taken from me, is how to work through a question, assessing, using what you know, using the scientific principles when they're stated or when they're implied. But just take that, run with it, use it, steal from me, please. Now I give you back to the very capable hands of Ms. Kristen Russell, and you all have a good Sunday evening. I'm going to go rest my voice, but I'll still be hanging around. So enjoy, Kristen. They're a fun group.
All right, I hope you guys had an awesome time. If you want to let me know what you thought of Brian, please feel free to do so. I always love watching him teach, so I feel pretty sure that you guys also did. So as promised, I want to talk to you guys a little bit about what to do from here. So we're going to switch on over back here, and what I want to work on first is coming up with a list of things that you guys probably want to include in your study plan. So go ahead and start dropping any of the things that you've thought of that you may want to include down in the chat. Tell me the things that you've thought you may want to consider adding. And we're just going to kind of keep track of a nice little list here. So tell me what you think we need to do. So one thing that I think is going to be super, super important, as I'm sure you guys realize at this point, is going to be content review. Okay, so do you think content review should come from maybe undergrad textbooks, going back to your old textbooks, reading through your old notes? Do you think that's going to be a good way to go about things? Well, knowing that this test is a mile wide, there's just so much different material tested on it, I think that's probably not the right way to go. So you want MCAT specific content review. And I see Diamond says practice tests. Practice tests are another really important thing to do. So in terms of practice tests, I think that the ideal scenario would be for you guys to be able to fit in 8 to 10 full-length practice tests. Now we do offer a free practice test. It's a shortened version. That one is still good practice, but it's not the same as full-length practice. So 8 to 10 full-length practice tests would be ideal. Megs, I like it. Actually learn physics. That's a good one, but just remember, you don't have to learn physics like you did as an undergrad, just the things tested on the MCAT. So that should make it a little easier. Okay, so some other things that are going to be good, and some of you guys might be thinking these, and I see some of them. So time management is something that really is going to come with lots and lots of practice. So practice tests are great, but they're not enough practice. So you're also going to want practice questions, ideally like by topic, so that you can practice things as you go. And then of course, practice passages, maybe even practice sections. So practice is huge. Okay, now what about a study schedule, like by week? I think this is super important for everyone and something that is not often done. But it's really easy to kind of forget that you need to build this in around things that are already in your schedule, right? So tell me in the chat how many hours per week you guys are going to be able to study. Because remember from the beginning, when I said 350 hours is your total study time. So how much can you study per week? I bet some of you can maybe fit in almost full-time studying, 30 or 40 hours a week, whereas others of you might only be able to do 5 or 10 hours a week. And that's going to be really different. And there's not a right or a wrong way to do this. You just want to make sure that your study schedule is built for you. So yeah, Francis, you're right in the middle at 20 hours. So first you're going to build in the things that you for sure have to do. So your classes, if you have a job, your volunteering, your shadowing, those kind of things. Then you're going to build in any, personal obligations you have. Maybe you have family dinner, or you do something with your significant other. Like, you can still have somewhat of a life, even though it may not feel like it. Then you're going to build in your study time. You want to actually block off time on your calendar. It's a lot easier to avoid procrastination if you do so. I'm a procrastinator, like, all the way. I was just telling my fellow teachers before class started that I still am not finished with my texts, and they're due on Tuesday. So I'm a procrastinator. I promise you I know. I was exactly the same way when I was studying for the MCAT. I would try and procrastinate if at all possible. If you know what you have to do each day, it's a lot easier to avoid that, because when you see, okay, if I don't do it today, then that pushes to tomorrow, and the list keeps growing and growing and growing, it's a little bit easier to avoid wanting to push it off. So these are some of the things that I think are really, really important. The last one is strategy. And after seeing Brian teach today, I think you can see that strategy is a big part of this. Even if you know tons and tons and tons of content, if you're not approaching the questions the correct way, it's still really easy to fall for traps. So strategy is a big piece. Now, when it comes to the right way to actually go forward and study for the MCAT, there's not really just a one-size-fits-all. It's going to work for every single person. I'm sure the way that Brian and I studied versus the way that Nzinga and Nikolai studied and Carrie studied, it's all a little bit different. But there are some things, like the things on this list, that all of us did. Now, I want to show you the different options that we have, and I want you guys to ask yourself a couple of questions. Do you learn well from a book? Do you study well on your own? Or do you do better studying in groups or having a study buddy? Do you prefer to have a tutor? Or do you like going to class? Is that how you learn? These are the types of things you're going to need to figure out to decide what is the best fit for you. So let me walk you through the different options that Kaplan has for you to prep with us. And I will also share with you guys some of the discounts that we have available. Okay, so first off, we have 3 different tiers of prep and 3 different delivery methods. So the basic prep is MCAT prep, and it is extremely comprehensive, though. There's really nothing basic about it. It comes with the 12 class sessions that are 3 hours each. You get MCAT channel, you get science content review videos, which all 3 of those are teacher-taught pieces of material. So some of them can be recorded, some of them can be live, depending on what your preferences are. But that's all content and strategy that's not being read from a book. That is watching a teacher teach it. We also have tons of practice tests. There are 11 Kaplan practice tests, and then we have all of the AAMC materials, including their 4 practice tests. Also, their section bank and the question packs, which the AAMC material is something that you absolutely need to plan to do. I mean, just thinking, okay, well, we need to study the way the test maker writes the test. then of course we definitely need to study the things that the test maker releases. Some of you may already have the Kaplan review notes. I highly recommend those. They do come with questions at the end of each chapter. They're great to see if you've kind of understood the material, but you are going to want more practice than that, and we offer tons more. We have QBank, which has over 1,000 questions. We have section tests, full lengths. We have passage-based questions for almost every chapter. I mean, just the list goes on and on. Now, regardless of what type of format class you have, all of the formats come with on-demand access to your lessons, meaning you can watch them anytime you want. Now, let me go through the different formats. So self-paced, this is working at your own pace. This is watching the lessons whenever is convenient for you, and you're doing that via the on-demand lessons. So it's just a recorded lesson, you're watching it. Now, live online is like similar to what we're doing right now, a little bit different. It's in our Adobe platform. So in that platform, we have a private Q&A, we have a public chat, we have different polls. So, you know, similar to what we've done today. And then you have an on-camera teacher and off-camera teachers helping. Then we also have this is what you guys might have been used to in the past, although some of you guys could have done online classes. So those are the 3 different types of prep options, and those are available for MCAT Prep and Prep Plus. So Prep Plus, in addition to everything that I mentioned for prep, also comes with one-on-one coaching. So that means that you're going to have 2 to 3. If you're self-paced, you have 2. If you're live online or in person, you have 3 one-on-one coaching sessions. So you're going to meet with your coach at the very beginning of your course, towards the middle, and then towards the end if you have that 3rd session. Each of those sessions is an hour. And you really can start to tailor your prep to yourself, ask questions, figure out how to review a full length. All of those things are going to be super important while you're prepping. Then we have private tutoring. Private tutoring is like the Lamborghini of test prep. It is great for those of you that know that this is something that has really worked well for you in the past, if you know that you really need some one-on-one attention. Now, the thing that I didn't mention that comes with private tutoring and Prep Plus is something I kind of wanted to circle back to. So if you do Prep Plus or private tutoring, you're also going to get the Biochem foundations, and you're also going to get the Behavioral Sciences foundations. Now, this is one of those things that if you have not had Biochem, if you haven't had psychology or sociology, these are amazing. They come with Prep Plus and private tutoring, but if you are an AMSA member, the American Medical Student Association, you can get the Biochem Foundations for free. You'll just need your 6-digit AMSA member number. So I bet some of you guys are AMSA members, and that's a pretty awesome discount. You can also get 10% off using your AMSA membership, right? So it's pretty cool. It costs $75 to join for life. It is not associated with Kaplan, but we do have a partnership with them since lots of our students are, of course, going to be members, which makes sense. Now, it does have to be the national membership. Some of you guys might have like local chapters at your school, but if you've paid the national member dues, that one-time fee, then you can get the Biochem Foundations for free and 10% off. Now, we do also have some other discounts going, so I know we're going to share some of those in the chat. We have military 15% off. You can get $200 off just for attending tonight. So you kind of want to figure out which of those discounts is going to get you the most money off, and that's the one that you're going to use. So one more I want to talk about, and that is called Starting Line. This one is a tuition assistance program, so it can get you up to 65% off of a class, anywhere from 25 to 65. There are some criteria that you guys have to meet. So number 1, you need to be a current student. Number 2, you need to have a GPA of 3.0 or higher. And I bet a lot of you have that GPA. The third one is that you need to have an EFC score of 4,000 or lower. So EFC is expected family contribution, and it's calculated on your FAFSA. So if you've applied for student aid in the past and filled out FAFSA, then you can go onto your FAFSA website, pull up student aid report, and you'll find it in the top right-hand corner. So we'll drop the link to apply for Starting Line in the chat as well. So a few different discount options available for you. I also wanted to mention that with any of these discounts, while you can't stack them, you will be able to use a payment plan and use the discount. The payment plan is going to split the class into 3 different installments that you're going to pay over 3 different months. And then one other thing that's pretty awesome about the class you get a free repeat. No questions asked, you get a free repeat. So if you take the class and you really didn't get time to devote to it the first time, you had other things going on, you can take it again for free. Or let's say maybe you do attend every class and you get tons out of the class, but you're still a couple points away from your target score. You can take the class again for free. It's a huge benefit. We have lots of students that take advantage of that for a number of different reasons, but it's wonderful to have that kind of security blanket there, just knowing that you can take it again if necessary. Ultimately, we want all of you guys to get into medical school and get the MCAT scores that you want. That's what we're here for. So if you guys do have other questions, please let us know and we'd be happy to help out. I want to finish up tonight by showing you a couple of our upcoming MCAT classes. So these are all our live online classes. You can see that we have a mix between weekend classes, we have weeknight classes, we have once a week, we have twice a week, we have 3 times a week. So lots of different options available for you. If you want to take a look at the full schedules, you can go to captest.com/enroll/MCAT to see more. Last thing I wanted to mention is the winner of our raffle for today. It's a $50 Starbucks gift card, and the winner is Neha Gupta. We will be sending out an email to Neha as well. If you're here, though, congratulations. Thanks for sticking around. That is it for tonight. We're going to go ahead and wrap up, and we would love for you guys to come attend another of our free events. So we will see you next time.